do that. So remember to remind me if you see me mess up. Make sure. Okay. All right. So PS6 is due end of this week here. And then midterm we'll review on Tuesday, and we'll have the midterm on Thursday. And you can bring one sheet of notes, front and back, handwritten or printed out. Any questions or problems about anything? Yes?
I was wondering if you could go over how the congruent works for modular. So I think it's like the x prime and the y prime example that you have to like the
Okay, so all right, so you're asking about congruence?
Yeah, I think it was like you said that you could rewrite x
Okay.
as x prime.
So if x and x prime are congruent, Modian, and just to save time, I'm going to assume everything's Modian here, so I'll quit writing it. And if y is the same as y prime, well, that's not right. Y prime Modian, then there are various rules. For example, x plus y is congruent to x prime plus y prime. That's just saying you can substitute equals for equals, essentially. You can substitute congruent things for other congruent things. So, for example, if we want to know what 100 plus 200 is, and we're working mod 3, well, you could add 100 and 200 and get 300, and you can see that's 0, mod 3. But how can you do it with the substitution rule?
You could do like 100 mod 3 and 200.
You could replace 100 with 103 if you want to, but you can also place 100 with 100 mod 3, which would be 1, and 200 mod 3, which is 2. And add them and take that mod, and you get the same 0. So you can replace equals with equals. Same thing here. xy is congruent to x prime times, x times y is congruent to x prime times y prime. And x to the y is congruent to x prime to the y. Notice it's not congruent necessarily to x prime to the y prime. So that's bad, but that works. Is that good? Any other questions? Yep.
So one of the examples in the slide was 5 to the negative 1 mod 8.
Mm-hmm.
How did you get 5 from that?
Okay, so it was 5 to the negative 1 working mod 8. Okay. So when you see a question like that, you're being asked what is the modular multiplicative inverse of 5? In other words, you're looking for something so that 5x is congruent to 1 mod 8. So the only possible answers are 0 through 7, because we're working mod 8. I mean, there are other answers, but they're all congruent to some number 0 through 7. So 0 is never going to work. You're not going to get 1 by multiplying something by 0. 1 will only work if you're trying to find the inverse of 1. So really, you just have to consider the numbers 2 through 7. So you just try them. 2 times 5 is 10. That's not, that's 2 mod 8. 3 times 5 is 15. That won't work. 4 times 5 is 20. That's no good. 5 times 5 is 25. And 25 divided by 8 has a remainder of 1. So 5 times 5 is 1 working mod 8. Now, we're about to see an algorithm for doing it, but for small numbers like this, it's much easier just to do it the way I just did it than to try to use the algorithm. Other questions? Yes?
On, I think it was like PS6.3, it was just, one of the question was like, how can the Dijkstra algorithm achieve an upper bound that's equivalent to the bounding towards algorithm? And it was talking about insertion and deletion, where like insertion was O of 1, could be O of 1 or O of B, and deletion could be O of 1 or O of B, and or they both want B. So it was just like asking how you would achieve the same upper bound complexity as bounded chords. And so I was just confused. Do you take like an amortized analysis of like delete n insertions because I feel like they're roughly the same. Like,
Yeah, I could barely remember that question, so. Is your question what I'm asking, or how to do it? Or,
yeah, just like how to go about it. Like,
I think you had a very helpful slide on Dijkstra's analysis, and we know Bellman-Ford's end behavior, and basically what you have to do is what the behavior of add and delete have to be in order
Okay.
to get it to be equal to
Okay.
Bellman-Ford.
so, yeah, what he said.
okay.
In case you didn't hear what he said, the idea is we looked at two different ways of representing priority queues that led to different complexity results for Dijkstra's algorithm. And so this is just playing that same game again, except your goal now is not to make Dijkstra's as fast as possible, it's to make it as bad as Bellman-Ford.
Right.
So you need to pick which, how bad the priority queue would have to be to achieve that, essentially. So look at the slide where I did that analysis. Yep.
So for the CAPS problem, I was using Java and I'm getting fine with it.
Okay.
And I think that I implemented a priority queue using binary queue with long initialization.
Okay.
I'm wondering if you have any advice for
Okay. First, just a couple comments. I would recommend using Java's priority queue, first of all, because that's the hardest part of the assignment, would be implementing the priority queue in the first place. Because not only do you have to, the problem is that update operation. You have to get the update operation efficient. Maybe you haven't. So when you go to update something, how do you find the thing you're updating?
well, I just have an index array like
Okay, so you do what I did. Okay, so Java has one and C++ has one. The problem with both of those, as I mentioned, is their update operation is linear time. And the workaround I gave is just forget that it has an update operation, and we want to update something, just insert it again with the lower priority. So that then the same thing will be in the queue twice. Eventually the smaller one will come out first, and at that point you got to remember that you have to have a set somewhere to keep track of what you've already taken off the priority queue, so you can ignore subsequent things that come off. If you're working in a different language, I'm okay with you just finding an implementation of a priority queue and using it. Okay, so if like using C#, which does not have a native priority queue, you can use another implementation, just cite it, because I'm mainly interested in Dijkstra's algorithm. But as for your question, it's hard to say without seeing your code, but I'd be happy to look at it. Any other questions? Okay. Here is where we left off last time. Modular multiplicative inverse. And so we already looked at, in fact, that third example right there I just talked about. So a modular multiplicative inverse is the problem of given a number A and a number n, two integers, we want to find an x such that the product of A and x is the same as 1 working mod n. It's the same idea as modular multiplicative inverse over the regular real numbers, except there it's you just take the reciprocal and you've got the inverse. Here it's a little trickier. Okay. We could also pose a problem of finding multiplicative inverses, forget the modular part, over the integers. But it wouldn't be very interesting because the only number that has an inverse, the only two numbers that have inverses, are 1 and -1. None of the other numbers have inverses. But with modular multiplicative inverse, there are cases where the inverse does not exist. So for example, 4 does not have an inverse mod 6. 4 times 2 is 8. That doesn't work. 4 times 3 is 12. That doesn't work. 4 times 4 is 16. That's not going to work, and so on. 4 times 5 is 20. And you can prove that an inverse exists if and only if A and N are relatively prime. Only if their GCD is 1. So you see all of these, 2 and 3, don't have a factor in common. 4 and 7, 5 and 8, 9 and 11. But 4 and 6 do. They have a factor of common 2. So 4 does not have an inverse mod 6. So we're about to look at an algorithm for computing the modular multiplicative inverse, which is key, another key to learning how public key encryption works. But any questions about this before I move on? I'm always surprised, even after talking about this for several days, that students remain that will answer a question like 5 inverse mod 8 is 1/5. Okay? Don't do that. I'm not asking for a fraction. It's another integer. Okay. So here's what looks like kind of a random fact. If you've got some d, some integer d that divides both a and b, and you can write d in that particular form, ax plus by, then it turns out that d is the GCD of a and b. So this screwy fact turns out is how we're going to base our algorithm. So you're given d, a, and b, and you want to find x and y, essentially. Well, let's look at some examples. So there I'm giving you d, a, and b. So what x and y will make this work out? So that a times x plus b times y is equal to d. Now this isn't modular, by the way. This is just plain old integers. So what do we have to multiply a and b by so that when you add them up you get 1? Yes? Either one of you. Okay, you're saying -3 and 5? Okay? So -3 and 5 would have worked. Right? You would get -24 plus 25 would be 1. This works as well. X times 2 is 16. 5 times -3 is -15. Add them together, you get 1. Okay? And since you can do that, since there's a way to combine, since first of all, d divides both a and b, and there's a way to combine them so that you, a and b such that you get d, that means that d is in fact the GCD of 8 and 5, as you can see. Now, what about this? 30 and 16, and d is 2. How can we, what's our x and y here? So make -1 and 2, yeah? -1 and 2 do it, and that means that 2 is a GCD of a and b, which we already knew. All right, now, proof turns out to be pretty simple. First of all, d divides both a and b, so d has to be less than or equal to the GCD of a and b. I mean, d is a divisor, so it can't be bigger than the greatest divisor. That direction is pretty easy. And here's another one. So GCD of a and b is a divisor of both a and b, right? Because it's the greatest common divisor of both of those guys, so it's going to divide both of them. And if it'll divide a and b, it'll have to divide, it'll divide ax plus by, because it'll divide this and it'll divide that. It'll divide a multiple of a, it'll divide a multiple of y, b. So it divides that, and that's equal to d, so it must divide d, so it has to be less or equal to d. So put that together, you've got that d and GCD of a and b are the same. All right, so we've got the fact, we've got some examples, we've got the proof. Now we need an algorithm. But first of all, what does this fact have to do with finding inverses? Modular multiplicative inverses, that's what we're after. It seems curious that there's this fact right here, but it doesn't even mention modular arithmetic. Yeah, Bruce?
D is 1, and that's what you're searching for, so you just need to find x and y.
Okay. So what he's saying is we can take this fact and turn it into something that will find what we need. So let's suppose we'd like to find the modular multiplicative inverse of A mod n. And of course, we have to assume that the GCD of A and n is equal to 1, or there wouldn't be an inverse. All right, so we're trying to find the inverse where 1 exists. Well, that means one way to do that is to find x and y such that ax plus ny is equal to 1. Now, where did that statement just come from? How do we know that x and y exist? So, how do we know we'll be able to do this? Yeah, Bruce?
I mean, we could use the Euclidean algorithm to prove that they exist, and then just backwards Euclidean algorithm will give us those values.
Okay, so you're looking forward to the you're looking at the algorithm, but let's forget about why I wrote this here. Why do I know I'll be able to find an x and a y such that ax plus ny equals 1? Yep.
1 divides both a and n.
1 divides both a and n, and
It's the GC.
okay. Yeah, if 1 divides both a and n, then you're going to have this fact is going to hold. So that's just a setup for the theorem up here. So we know we're going to be able to find this. Because we already know that GCD is 1. So this combination has to exist. So since that combination has to exist, I'm going to take the mod of both sides. So I just took the mod of this equation, ax plus ny equals 1. I took both sides mod in. So they have to be the same. So mod in of ax plus ny, I turned into ax. How did that turn out?
There's ny mod n is 0.
Yeah. ny mod in has got to be 0. And then I got 1 there. So I've got this equation. Ax is the same as 1 mod n. Okay? So let's let me just point something else out. What does this equation tell us? Let me just back up. From this fact here, we know that there's going to be a solution to this equation. Since there's a solution to that equation, there's going to be a solution to this equation. I just take both sides mod. But what does this equation tell you? What is this equation saying about x? Well, we know it exists, but what does it what properties does x have? Yeah.
That if you multiply it by a and then mod it with n, then you're going to get 1.
Right. It's an inverse. This is just saying that x and a are inverses. So this is given. From that, we know that this equation can be solved. And when we solve it, when we solve it for x and y, the x that we find will be the inverse of a. So to find the inverse of a, we just need to solve this equation. So we can find the inverse of a. We don't have to do modular or anything. To find the inverse of a, we just solve that equation. So let's see how that works. So suppose we want to find the inverse of 3 mod 13. So there's it. We're going to say, okay, their GCD is 1, so we know there's going to be a solution to the equation 3x plus 13y equals 1. And x is going to be when we solve it, x will be the inverse of 3, mod 13. So what's the solution to this? What's an x and y that solves this equation? Yeah?
9 and negative 2.
Okay, say 9 gives you 27, and negative 2 gives you 26, yeah? I found a different one, it looks like. I mean, there are lots of solutions. Here's negative 4 and 1. Okay? That's negative 12 plus 13 is 1. So then, what is the inverse of 3? Over here it said, if you solve this equation, x will be the inverse.
So 13 minus 1 would say 9.
So negative 4 is the inverse of 3. Okay? Let's try that out. What's negative 4 times 3?
12.
Negative 12. Let's add 13 to it to get it into the right range. You get 1. Okay. So negative 4 is the inverse. But we always want to write things in the range from 0 to n. So let's add 13 to that, and we get 9. And your solution, we've gotten that without that step. Okay? So 9 is the inverse. So the bottom line is to find a modular multiplicative inverse. We first we got to make sure the GCD is that it exists, like doing the GCD. We set up this equation: 3x, where 3 is the thing we're inverting, and 13y, where 13 is the modulus, equals 1. Solve for x and y. X is the inverse. Okay, here's the algorithm that does it. It's called extended Euclid. It's exactly, it's structured exactly like Euclid's algorithm, EE up here. So look at what EE does. It takes in an A and a B, and it returns an x and a y and a d, such that d is a GCD and ax plus by equals d. So it returns a triple, 3 things. It returns returns the x and the y that makes that equation hold, and the d, the x, the y, and the d. So let's ignore, just to get a first look at what's going on here. Just, you see it returns a list of 3 things, x, y, d. Let's ignore the x and the y part and just look at the d part, which is the GCD part that's being returned. This is just Euclid's algorithm. It's saying if b is 0, the GCD is a. Otherwise, we return the GCD of b and a mod b. You see right there. So it's, at its heart, it's Euclid's algorithm. The extended part is what computes the x and the y. So look at the base case. If b is 0, it says return 1, 0, a. Does that make sense? X is 1, y is 0, and the GCD is a. Right? Suppose you're taking the GCD of 7 and 0. What would this thing return?
7.
Yeah, it returns 3 things. What 3 things would it return?
7, 0.
1, 0, 7. So it's saying the GCD is 7, and it's saying that 1 times a plus 0 times b is that 7. And that's true. A was 7 and b was 1. And then the base case, in the recursive case, it's a little more complicated. You make a recursive call. You get back what I'm calling, you get 3 things back, x prime, y prime, and d. And this shows how you compute the 3 things that you return from the recursion. So there's a lot of, the bookkeeping is kind of intricate on this thing. And then this is the inverse algorithm, which is if you want the inverse of a and n, you use extended Euclid to compute the triple x, y, and d. If d is 1, meaning that that the GCD is 1, then x mod n is the inverse you're looking for. Otherwise, there's no inverse because the GCD wasn't 1. Now, you will be, I'll give you a preview. In problem set 7, one of the things you'll be doing in the caddis problem is implementing this algorithm. And implementing the algorithm is a lot easier than trying to trace through it on paper. It's, there's a pseudocode. It's not hard to do as long as you avoid integer overflow. But we're going to trace through it on paper once. And I mentioned last time, there are a few sadder sights than watching a student try to trace through this during a final exam, trying to compute the inverse of 5 mod 8 or some such. So I don't recommend coming anywhere near this on a final exam, trying to do a computation using it. I'm just showing you the algorithm exists. So let's see what's going to be involved. We call extended Euclid of 3 and 13, presumably because we want the inverse of 3 mod 13. What recursive call is made? We're certainly not at the base case. So what recursive call gets made? Yeah, this is just straight, until we get to the bottom of the recursion, it's going to look just like Euclid's algorithm. So we're just down here in the recursive case. It says b, comma, a mod b. So it's going to be E of 13, 3. And we're going to make that call. We're going to get back x prime, y prime, and d. Well, let's skip ahead to the call. There's EE of 13 and 3. What recursive call is it going to make? Yeah, 3 and 1. Okay? What recursive call will we make to solve that? One and 0. And that's the base case. So now let's work our way back up. What's going to be returned by EE of 1 and 0? Yep, 1, 0, 1. Which means that from the standpoint of this stack frame, x prime is 1, y prime is 0, b is 1. So you got those. You got what you're supposed to return here. So what we're going to return? So you're returning a triple. What will the first thing we're returning be in this case? Okay, it says return y prime, and y prime is 0. So return 0, comma. Let's look at the last thing. The last thing we're going to return is 1, because that's the GCD. The middle one is the hairy one. So let's see. X prime is 1 minus, this has got to be an integer division where you throw away the remainder, but it doesn't matter because y prime is 0. So it's going to be 1 minus 0 is 1. So what do we come up with? 0, 1, 1. Great. And that becomes the x prime, y prime, v at that second stack frame. And we'll go through the same calculation again. This time, I'll just show you what the answer is so we can confirm it. Okay, the first number is 1 because y prime is 1. The last number is 1 because that's what v is always. And then we have to take x prime, which was 0, and subtract a divided by b, which is 4, times y prime, which is 1. So that's 4. So it's 0 minus 4, that's where the negative 4 comes from. Like I say, doing it in your head is even worse. But anyway, we get that. And if we do that computation, we return that. Negative 4, 1, 1. And the reason we're doing this is to find the inverse of 3 mod 13. So which of those three numbers is our answer? The first one. Negative 4 is the inverse. And then the final step would be to take that negative 4 mod in, which would give you the 9. That was what is the form we want to see it in. Okay? So there's the algorithm. So the important takeaway is that it's how you find modular multiplicative inverses, which is going to be important in a minute when we look at RSA. There's a proof. I'm going to skip over the proof of correctness. It's just a bunch of, it's not complicated, it's just detailed. So, are there any questions I can answer about this algorithm? Yeah?
Where does the x prime minus a over b times y prime?
Where does it come from?
Yeah, like how do you know that that's equal from the
That's how you know it works. I can't tell you how it was derived, how it was invented, but that proves that it's the right choice. I don't have any other intuition for you. This is an inductive proof that the Euclid's algorithm is correct. Okay. Any other questions? All right. So let's see. We've looked at modular exponentiation. We've looked at Euclid's algorithm. We've looked at extended Euclid's algorithm. All of those are part of public key encryption. One last piece we need are prime numbers. So here's the cool thing about RSA. It relies on all those algorithms that I just mentioned. It relies on modular arithmetic. It relies on modular exponentiation and greatest common divisor and Euclid's algorithm. And it relies on the ability to generate large prime numbers at random. Almost just stuff from number theory. RSA is just number theory used to create an encryption algorithm. And some of the number theory is thousands of years old in the form of GCD. Others what we're going to look at with prime numbers is hundreds of years old, 400 years old, most of which you would have looked at 50 years ago and said, this is only a theoretical interest. It's only of interest to pure mathematicians. It just goes to show you that you never know when you're discovering things, when you're doing research, what's going to turn out to be important. And this certainly turned out to be important. So let's talk about prime numbers. So prime number is an integer greater than 1 whose only factors are itself and 1. So we've got the primes are 2, 3, 5, 7, 11, and so on. And if it's not prime and it's greater than 1, we call it composite. So all the even numbers greater than 2 are composite, and many odd numbers are composite as well. So that's what I mean by prime and composite. Now, there was a question that was settled hundreds of years ago about whether there is a largest prime number, and the proof is kind of neat, so I'll show you here. So the proof is assume there are only k prime numbers. So we're just going to name them p1 through pk. And then I'm going to multiply all those prime numbers together and then add 1. So I claim that this number here cannot be divided by p1. It's 1 more than a multiple of p1, right? p1 divides this big product here. But if p1 divides a million, it's not going to divide a million in 1. Buy that? Okay? Same thing goes to your other primes. So none of these primes will divide this number right here. What does that mean? None of the existing prime numbers, or assume that these were all the prime numbers. We just constructed a number. None of those primes divide it. So either it's a prime number. What's the other possibility? This is either a prime number that isn't on our list, or what could it be?
Composite.
It could be a composite. That means it's got to have prime factors. Those prime factors aren't on the list either. So either way, it's either a prime number that's not on the list, or it's a composite whose prime factors are not on the list, because none of these numbers are factors of that big number, which contradicts our assumption that there's only k prime numbers. So RSA depends on being able to generate quickly at random a long prime number that no one else has ever generated, basically. You've got to be able to create a completely random one that is extremely unlikely that anyone else has ever generated in the course of doing RSA as well. So at least it's reassuring that there are an infinite number of prime numbers to choose from. This wouldn't work at all if at some point there stopped being prime numbers. Right. Now, let's think about how would you test the way you generate a random prime number. Let's say you want a 2048-bit prime number. So you just generate at random 2048 bits, and then you test it to see if it's prime. And if it's not prime, you generate another random number and try again. And if you have a good random number generator, and the ones that you use in practice in your programming languages are not good for this. They're not really random number generators. If you have a cryptographically secure random number generator, then you can generate prime numbers this way, random prime numbers. But how do you test? How do you test to see if a number is prime? Yeah? Okay, so you factor them. Is that what you said? Okay? You can try factoring the numbers. So you got a prime number, you try to factor it. Well, there's a catch. No one has ever found a factoring algorithm that isn't exponential. This says exponential in n. N's a number of bits. So to factor an n-bit number takes exponential time with current technology. So factoring isn't going to be the solution. Yeah?
Has it been proven to be that time?
It has not been proven to take that much time. It's an open question. And in fact, the security of public key encryption is based on the assumption that factoring can't be done quickly. If you discovered a fast factoring algorithm today, I wondered what would happen. It would be a revolution. Your life might be in danger. Because you would hold the key to cracking the entire financial system. Okay? So it's kind of a scary thing that all the security of our e-commerce system depends on the assumption that there is not a fast factoring algorithm out there. So what else might you try? Yeah?
You can just go from, like, what is it called, C to Neurosteam's algorithms, and just go from I up to the square root of n.
Okay, so you do a bunch of trial divisions. You say, does 2 divide it, does 3 divide it, does 4 divide it, does 5 divide it, up to the square root. And you can skip, you can try dividing by 2, but after that you don't need to consider any even numbers. So you can think about making it better. So that's called trial division. You don't have to go bigger than the square root of the number because that's just, that's the largest factor it can have other than itself. Well, the problem is that requires the square root of p divisions. Okay? But p, remember, we got to express complexity in terms of the number of bits. And so p is 2 to the n. If p consists of n bits, then p is roughly 2 to the n. So this algorithm is 2 to the n over 2. It's exponential. So the problem is there are an exponential number of things to test. So if your number is like 2 to the 100th power, roughly, you've got to do 2 to the 50th trial divisions. That's 2, no way. And we're not even talking, in RSA you're talking about 1,000-bit primes or 2,000-bit primes. So that's a common way to do it, but that's not going to fly either. Okay, now, until 2002, I used to teach this class before 2002. Not only was there no efficient way to test the factor number, there was no efficient algorithm to even test for primality. But in 2002, 3 computer scientists in India, a professor and 2 undergraduates, discovered what's known as the ATS algorithm. And when they first published it, it was an O of n to the 12th algorithm. And people looked at it, and it gradually got improved with O of n to the 6th. So there is a polynomial time algorithm to determine if a number is prime. But that n to the 6th kills it, makes it too slow. So that's not what's used in practice. In practice, what's used is a probabilistic test because it's fast. So let me show you what's involved. It's based on Fermat's little theorem from 1640. So here we have almost a 400-year-old theorem, pure number theory, and it's how you use to generate keys for RSA. And here it is. What he proved is that if p is prime, then for every number between 1 and p, for every number a between 1 and p, a to the p minus 1 is congruent to 1 mod p. Okay? That may look off the wall, but you'll see it'll make sense in a minute why it's interesting. So let's just see what happens. What are we saying? Let's let p be 5. So what's Fermat's little theorem saying about the numbers 1, 2, 3, and 4? It's saying any a you pick in that range is going to have some property. So say you let a be 1. What's it saying? One to the 4th is congruent to 1 mod 5. And that's true. 1's always going to give you 1. It also means that 2 to the 4th mod 5, which is 16 mod 5, which is 1. Okay? It also works for 3, it also works for 4. You take any prime number, it'll have this property. So your prime number has 1,000 digits. Then every single number between 1 and that number is, you raise it to the p minus 1 power, mod p, you're going to get 1. Pretty cool. All right, let's let p be 6. 6 isn't prime, but you can still play the game. Okay? 1 to the 5th mod 6 gives you 1. 2 to the 5th mod 6 gives you 2. 3 to the 5th, 4 to the 5th, 5 to the 5th. So it always works for prime numbers. Problem is it sometimes works for composite numbers. Now, what if the theorem was stronger? What if it said, for a prime number, you do this thing, you always get 1, and for a non-prime number, a composite number, except for this case, let's say, throw this case out in 1, won't use 1. What if it was like this? You always got a number that wasn't 1. What would you have? How would this be a primality test? So it's just, Ignore this case. This case is uninteresting. So what if you had the property that for a prime number, you do this computation, you get all ones. For a composite number, you do this, you get all non-ones. Yeah?
You just check every number from 1 to the prime number.
He's saying check every number from 1 to the prime number, but if this were always 1, you just have to check 1. Right? You use 2 for example. You just raise 2 to the p minus 1 mod p. If you get 1, it's prime. If you don't, it's composite. That would be nice, but that's not how it works. All right, here's the basis of the test. We want to know if n is prime. So we pick some number between 1 and n, and we ask, is that number to the n minus 1 power congruent to 1 mod n? If the answer is yes, what does that say about the number being prime?
It's possible.
It's possible, it may be, it may not. We don't know. But what if the answer is no? Then it's not prime. So this is going to be the key step in our primality detection algorithm. We're just going to pick a number we want to see if it's prime. We're going to pick at random some number between 1 and it. We're going to do this single modular exponentiation and see if we get 1 back. And if we don't get 1 back, we'll say, it's not prime, and we'll go guess another one. But what if we do get 1 back? What does that mean? It may or may not be prime.
What's the advantage of having it be random? The number between 1 and 8. Between 0 and 8.
Well, it turns out in practice, it's not all that important. Because we'll see in a second, if you can use 2, 3, and 5, and if I'm getting a little ahead of myself, so let me get back to that. Yeah.
Approximately how accurate is it?
Okay, that's the key question. How often, when it says n may be prime, how often does a composite number fool this test? Suppose n is composite. You're going to get the answer, it's going to be equal to 1, right? Let's say you give it a composite number, and it turns out you do this test and you get a 1. What's the probability that it will behave like a prime number to you one back? You feed a composite number this and it says maybe prime. That's the key question. So let me just give you an answer. Suppose I told you that it's the probability with if you choose a random number and you do this test and the composite number says it may be prime, the probability of that happening is no more than 50-50. So no more than it won't fail. It won't fool the test more than half the time. Does that suggest a way to test for primality? Okay. Okay. So what about? Well, I'll do this. I've got some gigantic number I'm trying to test for primality. So I pick some random number, smaller than it, do the test, and it says maybe prime. And I know, okay, that answer is going to be wrong 50% of the time or less. So I've got a 50-50 chance of being wrong. Yeah.
Don't you just want to keep testing until you're in like a desired threshold
Okay.
of correctness?
Okay. So she said, keep testing until we're in a desired threshold of testing. So let's pick another random number and do the test. And suppose that again it says back maybe prime. What's the probability that I'm being lied to now? That it's actually composite and it's fooled the test twice. 1/2 times 1/2, which is a fourth. This is why the randomness is important because we make this argument that the probability has to do with if you choose a number at random, it'll fool the test at most half the time. If there's a pattern to the way we choose the numbers, then probability is different. Would you live with a 1/4 chance that your e-commerce encryption won't work?
No.
All right, let's do it again. We pick another number, and it says maybe prime. What's the chance that we're wrong, that we're being lied to 3 times in a row? 1/8. Is that good enough?
No.
Let's do it 100 times. Suppose you do it 100 times, and each time it says maybe prime. What's the chance that this number that we're holding is not prime?
1 over 2 to the 100.
1 over 2 to the 100th power. That is really tiny.
I trust it.
Okay? He said he trusted. What about the rest of you?
Yeah.
Okay? Thumbs down. Okay? Okay, so I'll say this to you that don't trust it. Why do you ever go outside? You may be struck by lightning. The probability that you'll be struck by lightning is bigger than that. Much bigger than that.
I'm not going outside ever again.
Okay? Yeah?
That's only
Should we be more concerned about an e-commerce thing going wrong? Not for me specifically, but for anybody involved in the e-commerce scene, because this is happening so often. So that specific encryption might be 2 to 100, but
Okay. But if we did 2 to the 100th e-commerce transactions, or if we generated 2 to the 100th RSA key pairs, we would expect one of them to go bad. Yeah. But 2 to the 100th is an unimaginably large number. It's larger than the number of subatomic particles in the universe. Yeah.
So, even though it's really large, we can never really be sure.
That's right. But what else can go wrong with your computer? That's more likely than that. But make it cause anything.
picking the same random number of
What?
like bit flip.
Yeah. You can get random things happen in your computer. A bit can be flipped. A cosmic ray literally can hit your memory and flip a bit. And that happens way more often than one chance in 2 to 100. There are all kinds of risks that we put up with just with computers where faults can happen far more frequently than that. And so whether you feel good about it or not, that's the way it's done. The prime numbers that are being used in RSA are chosen this way. I don't know that they even tested 100 times, but it's tested probabilistically till they can get reasonably sure, or incredibly sure that they have a prime number. Yeah.
I mean, so like with this, like you're not trying to have it be perfect, right? It's like the people that are going to be breaking it are going to be humans, right? So long as you can make the probability of finding like a bad key pair super low, then it's not worth your time anymore to like try and find that, right?
Right. Well, okay. So the key question is what happens if we use a number that's not prime in RSA, and it may be the case you don't notice at all. But it's going to be what'll happen is sometimes the key won't work. You'll encrypt something, you won't be able to decrypt it, or that's bad. Or you encrypt it and it's easy to decrypt, which is bad. So it's kind of unpredictable what effects it would have. I mean, it could have different effects. But the fact is, there's a finite probability that it could fail. We sort of unconsciously put up with probabilities like that all the time. Okay, so let me just go through this and then we'll take a break. So this is what we've been talking about. How likely a composite N will fool the test? First of all, we only have to worry in cases where A and N are relatively prime. Because if they're not relatively prime, then there will be no multiplicative inverse, and we won't be getting a 1 out anyway. So there are some numbers that fool the test every place they can. Okay? So 560, they're called Carmichael numbers. 561. They don't fool it for every number. They don't because they can't. You can't fool it like I just said if A and N are not relatively prime. But Carmichael numbers are as bad as they get. They fool the test for every relatively prime A, which is to say they almost always fool the test. Except for those Carmichael numbers, A will fool the test at most half the time. And there's a way to deal with Carmichael numbers. You won't go into it. There's a simple way to not deal with Carmichael numbers. And so there's the key thing. A will fool the test at most half the time. And so if you do the test enough times with different A's, you can become as certain as you want that you got a prime number. Yeah?
How do you pick, because you're doing this test on a whole bunch of numbers, how do you pick which one has, like, because does that make sense? You've done the test on a whole bunch of numbers.
Mm-hmm.
Which one do you pick?
Well,
The last one that you tested?
yeah. You pick one to test for primality, and you basically shoot at it 100 times, and if you don't kill it, then it's your prime number.
Oh, okay.
Right? It's got 100 chances to fail, to to fool you. If it if your composite number fools you 100 times in a row, then
I
you're out
thought
of
we were
luck.
picking different numbers each time.
No.
Doing those equally.
We're picking different A's each time.
Yes.
But we're testing n for primality. All right, let's take a break and then we'll continue with this. Okay. So here is our probabilistic primality test, and again, it's not dealing with Carmichael numbers. That's a another elaboration. This is going to be good enough for us. We just pick a number at random. Well, this is the beginning of it. We pick a number at random. We do the test. We pick k numbers at random. We do the test. If they all give us 1 back, we return true, otherwise we return false. Okay, and we decided the probability it's going to be fooled is no more than 1 over 2 to the k, where k is the number of tests we do. And we already said that. If you let k be 100, you've got a tiny chance that you've been fooled. We've talked about that, how you feel about it. Some of you are uncomfortable. It turns out, this is where I started to say, Prince, when you asked your question, you don't even have to pick. To a first approximation, if you just use 3 numbers, a, 2, 3, and 5, and did the testing, you wouldn't be fooled very often, even for hundreds of bits. So the test is good enough that for hundreds of bit long number you're trying to test, it's very, very, very hard to fool it, even if the only A's you use are 2, 3, and 5. So numbers that are certified as prime, just using those 3, are sometimes referred to as industrial strength prime numbers. I did an assignment once where I told students I wanted them to draw a graph. I said, create, just using 2, 3, and 5, see how often the test is fooled by a composite number. So they're sort of generating composite numbers and seeing if it fooled the test. And I didn't do it ahead of time. I just made up the assignment and asked them to do it. And then everyone turned in flat graphs. It basically never fooled the test. It was so good. So there's our test. Now, we have a test that'll work. The question, though, is how hard do we have to work to find a prime number? What if it's extremely rare? Suppose you want a 1,000-bit prime number, and it's there are very few 1,000-bit primes. Then we're going to do lots of testing and never find a prime number. So we need to know how common are prime numbers. What's the probability that a randomly chosen n-bit number is prime in the first place? And there's a prime number theorem due to Lagrange that just blows me away. I don't see how you possibly would conceive of this, let alone prove it. But here it is. We'll let pi of x be the number of primes less than or equal to x. And what he showed is that in the limit, as x goes to infinity, pi of x is x divided by the natural log of x. Wow. I mean, it's like, I think of, x divided by natural log of x is continuous mathematics. I think calculus or something. And prime numbers is discrete mathematics. Okay, well, let's then figure out what's the probability that k-bit integer is prime. And here's how I'm going to do it. In the theorem, I'm going to let x be 2 to the k. Right? Because 2 to the k is, it's actually a k plus, it's bigger than all the k-bit prime numbers. Than all the k-bit numbers. So 2 to the k. How many prime numbers are less than or equal to 2 to the k? Well, what's the theorem say? It's just 2 to the k divided by the natural log of 2 to the k. And you do a little bit of mathematics. You get, well, that's approximation. We do another, because that's only true in the limit. What have I did here? Okay, so we've got this approximation. What did I do here? Right, I divided pi of x by 2 to the k because I want the probability. So if this is the number of primes, that's the number of numbers. That's the number of k-bit numbers. So I do that division. I get that. I simplify down. It turns out it's about 1.44 divided by k. So let's see here. What if k is 1,000? Let's approximate this with 1. So if you want a 1,000-bit prime number, you pick one at random. You got a 1 in 1,000 chance that you picked a prime number, roughly. It's a little better than that. So yeah, it's going to take a bit of work. You're going to have to test about 1,000 numbers before you find a prime one. And the bigger k gets, the harder it becomes. So if k were 1,000,000, you'd have to test 1,000,000 numbers before you found a prime number. but it's not like they're very rare. They're common enough that we can expect to find one, just picking at random. And of course, we can double the odds by never picking an even number, so got that working with us. Okay, so that's a story about prime numbers, and that gives us all we need to do RSA. So let's do RSA. So let me set up the stage here. We're going to talk about cryptography. We're going to have Alice trying to communicate with Bob. So Alice has a message X that she wants to send to Bob. So what she does is she has some encryption algorithm that I'm calling E. So she takes her encryption algorithm and encrypts it and produces X prime. That's the encrypted message. X prime is transmitted over the web, the internet. Bob runs a decoder, runs D of X prime on it, and recovers X. So that's just a general diagram of what encryption looks like. We're going to assume, you always assume that there's someone in the middle we call Eve, because Eve is an eavesdropper, and we assume Eve has access to X prime. And furthermore, we assume that Eve knows the algorithm that Alice and Bob are using. So clearly, if it's this simple, if she knows the algorithm, she could just run D herself and decrypt it. So we need to make it easy for Alice and Bob to communicate, but hard on Eve to break the code. So here is an absolutely secure method of encryption. It's perfect, cannot be broken, and is not used in practice. Let's see why. So all we have to do, we want to send an n-bit message from Alice to Bob. Alice and Bob agree on a random n-bit key. So they just pick n random bits. That's easy to do. Flip a coin n times. And to encrypt X, you take this random string R and you XOR X and R. And to decrypt, you do the same thing. Okay, that's called a one-time pad. So let's say you want to encrypt X. So there's R. I just picked some random numbers. We do a bitwise exclusive OR, and that's what you get. So 1 XORed with 1 is 0, 1 and 0 is 1, 1 and 1 is 0, and so on. 0, 0, 0. So you transmit X prime, and then that's what Bob gets. And then Bob just does the same thing. Bob takes X prime and R and XORs them together and recovers the original. Works every time. So first of all, why is this secure? Why do I say it's the imperfect way to do encryption? Yeah?
Because you can't, assuming that you don't have X in the first place, you can't drive R.
Okay. So basically, we're encrypting every bit separately, right? Every bit in R was chosen at random. And so this takes 1, and if we, based on a coin flip, 1 will either encrypt to 0 or to 1. And every bit is independent. Figuring out what the first bit is doesn't help you pick what the second bit is. It just depends. You see a 0 in the message, there's a 50-50 chance that that 0 in the plain text was a 1, and a 50-50 chance that it was a 0. It just depends on the coin flip that was used to generate R. So there's no information to go on. Best you can do is try to guess R, and there's too many versions of R to guess. But why is it not used in practice? Yeah.
So then your encryption is as large as the data?
Say what?
Your encryption, whatever you're encrypting by, will be as large as the data if you're doing a bit for bit.
Right. You're limited to the length of R. But so what? We'll generate a giant R. Yeah?
Your encryption is based on just that R. So if someone finds out R.
Okay. If someone finds out R, we're in trouble. And you want to add?
If you have both X and the encrypted X, you can drive R.
Okay. So if you happen to know the plain text, you can derive R. Right? If you've got both X and X prime, you can derive R. You just XOR them together. But also, how does Alice get R to Bob? How did Alice and Bob agree on R? Does she send it over the internet? Eve is in the middle. Eve's going to intercept R. So the problem is key transmission. And the other problem is you can't use a key more than once. If you use a key twice, it starts to break down. So you have to use a separate key for each communication. So the problem is, to send a secret message, you have to send a secret key first. Now, this technique was used in the Cold War. It wasn't used digitally. It used the same idea, but it was alphabetic. Basically, an alphabetic substitution where every character was substituted separately. There was a separate way to encrypt each letter in the message. So it was used to send, say, a message from U.S. to the embassy in Moscow. And to do that, there were code books. And the sender had to have the code book, and the receiver had to have the code book. And they had to be agreed. This first message that got sent would use code number 1. And they'd throw that away and use code number 2, and then code number 3. How do they get the code books from here to there? Yeah?
Someone had to physically transfer the book to
Yeah.
the embassy in Moscow.
Right. The book went in a briefcase. Briefcase is put in the diplomatic pouch and handcuffed to the agent's wrist and flown to Moscow. And the Russians did the same thing. But that's too slow nowadays. So this is perfect, but not used because of the key transmission problem. See, here's the problem. Let's XOR. Okay. If you do the math with XOR, you find out that if you intercept an encrypted message X prime and another encrypted message Y prime that use the same key, then it turns out what you've got is X XORed with Y. And you can start recovering information that way. There's just, the random key is missing now. You just got two messages that were XORed together. And that's not going to be secure necessarily. Okay, so the problem is key transmission, and the keys have to be long. Imagine streaming a movie that you wanted to encrypt with a one-time pad. Right? That's a big, long key to XOR the movie with. Now, I'm going to come back and talk about AES later because I want to make sure I talk about RSA today. Okay, here's RSA. The game we're playing now is to encode, well, there are a pair of keys. So for Alice to communicate with Bob, Bob has to have what's called an RSA key pair, that consists of a public key and a secret key. So P sub B is Bob's public key. S sub B is Bob's secret key. And for Alice to send a message to Bob, she has to know Bob's public key. And she doesn't have to know the secret key, though. So she runs the algorithm and encrypts a message X with Bob's public key to create X prime. X prime goes over the wire, Eve intercepts it. Bob takes the encrypted message and decrypts it using using his own secret key. Now we assume that Eve in the middle has the encrypted message, and also that Eve knows that RSA is being used, and also Eve knows Bob's public key. It's believed that knowing all that stuff, it's still extraordinarily difficult for Eve to break the message. You really need the secret key. So this solves the point behind RSA. So AES, which I skipped over, involves a secret key that both ends have to have, but you can reuse it. You still got the key transmission problem. This method, you don't have to transmit the key. You don't have to transmit a secret key. Bob generates a pair of keys, the secret key and the public key, and then he can put the public key on his webpage. People do it. He can send it out in email, whatever. And then anyone that has it can send a message to Bob, but only Bob can read the messages because only Bob has a secret key. So let's see how it works. And this is all stuff I just said. So typically we're talking about keys of length 2048 bits or more nowadays. And I'm going to come back with this, so we're going to miss a week because of the midterm and the review. I'll come back to it, but I want to get to the basis of the algorithm today. We'll come back to these slides next time, or in 2 weeks. Because I want to show you how all this fits together. All the stuff we've been doing fits together. and also because the next CAS problem involves this. So here's how RSA works. First thing is we select two distinct prime numbers, P and Q. Right? And we saw how to do that. Typically, we're talking about 1024-bit primes or longer. 10 years ago, I would have said 512 bits or longer, but state of the art in factoring has improved enough that it's no longer recommended to use primes that small. So nowadays, this is the recommended length. So that's about 300 digits or so, 350 digits each. Whoops. We multiply P and Q. We know how to do that. Now we have N. N is the modulus. Okay, we're going to call N the modulus. Then we're going to construct a number called phi. That's just the product of P minus 1 and Q minus 1. That's not hard. We then got to find an E, a small integer, that is relatively prime to phi. Okay? So we want to find a number such that the GCD of E and phi is 1. So how are we going to do that? We got phi, how are we going to find an E that works? Yeah?
Can you just pick another prime number?
Well, E doesn't have to be prime.
It could be though.
Yes. But we don't have to restrict ourselves to primes. Yeah.
If phi is divisible by 2, if phi is divisible by 2, don't do anything. If it isn't divisible by 2, use 2.
Okay. Yeah, sure. Two will work if phi is odd. But what if phi is even?
We'll then test with 3 and then keep going up.
Yeah. The basic idea is you just pick the smallest number you want to start with. And typically you don't start with 2. In real systems it might be like a 8-bit number or a 16-bit number or something. And you just start testing. And you don't have to test long before you find one that works. So you just find, you don't have to be picked at random. You just find one that works. You write a loop that tests numbers till you find one that works. That's called the public exponent. Then we choose D to be the multiplicative inverse of E mod phi. All right? There's our extended Euclid algorithm. So we use GCD to find repeated uses of GCD to find E. Then we use our extended Euclid to find its inverse D. And that's called the private exponent. And now we're done. We've got N, we've got E, we've got D. And the public key is the combination of E and the modulus. So the public key is the exponent E and the modulus N. The private key, the secret key, is D, the private exponent, and the same modulus N. So what's the only secret here? D. What's the obvious way to attack this? E is going to have the public key. We'll assume that everyone knows the public key. What's the obvious way to attack this?
Is it the factorial method? Factorial n
Right.
basically.
All you have to do is factor in. If you factor in, you've got P and Q. That gives you phi. You know what E is. You can solve for D. So the only thing standing between us and the collapse of e-commerce is the fact that 2000, N is the product of two 1024-bit prime numbers. So it's 2048 bits, say. We're assuming that it's impossible, essentially, effectively impossible to factor such a number, such a large number. Okay? So let's see how the keys are used. It's very easy. Your message has to be less than N. So your message is some bunch of bits. So you chop it up into blocks, where each block is a number less than N. And N is so we're talking about like 2,000-bit blocks of numbers. And you just take X, the message, raise it to the power E mod N. And that encrypts it. And decrypt it, you do the same thing, but you use D. So it's just modular exponentiation to encrypt and to decrypt. So that uses all our algorithms. Modular exponentiation, GCD, extended Euclid, prime generation to get started in the first place. So let's do an example here. Let P be 3 and Q be 11. So what's N? 33. Now what's phi going to be? P minus 1 times Q minus 1, so 20. Okay, what's an E that'll work? Let's just start with 2. Does 2 work?
No.
Does 3 work?
Yeah.
Yeah. GCD of 20 and 3 is 1, so we'll use that. Now we have to find the inverse of 3 mod 20. 7. 7 times 3 is 21. So our public key is exponent 3, and then 33, and our secret key is 733. Okay? It's that simple. And there's a table that shows you what happens when you encrypt X using that key. So 0 goes to 0, 1 goes to 1, which tells you you better make sure, maybe you should compress your message before you send it or something, you know, because if the message is all zeros, it's clear what it was. Same thing for 1. We encrypt these things. This is what encrypts do. And if you do Y to D, you get the same thing back. So the way to think about RSA is it's doing what it's doing. But basically, it manages to map every integer in this range to a different integer. So have you ever used a code where you said, okay, well, I will send X when I mean A, and I will say Q when I mean B. You've maybe seen crypto puzzles like this, cryptography puzzles like that. It's called a substitution cycle, where you're substituting letters for letters. What's this substituting? So one way, you got the encryption table for the alphabet would be 26 rows. Each letter maps to another letter. A maps to Q, B maps to Z, C maps to L. So it'd be a table with 26 entries in it. What does public key encryption do? Yeah?
You're changing bits from one number to another.
It maps every 2000, and say we're using 2048-bit modulus. It maps every 2048-bit sequence to a different 2048-bit sequence. And while you can break a crypto quote by saying, this occurs a lot, I think it's an E. It doesn't work so well when your alphabet essentially is, each letter is 2048 bits. So it's a giant substitution table. The table will be too big to write down. So it's just computed by that modular exponentiation. Yeah?
Just and then basically number rules. When you multiply those two prime numbers,
Yep.
the n that you get, is the first factorization of that n always going to be the p and q?
Yeah, when you multiply two primes, the only two factors are the two primes. Yeah. Other than 1 and the number itself. Yeah?
So how do you determine the complexity of this argument?
Well, what's the complexity of encryption? Suppose you've generated the keys. What's the complexity going to be to actually do an encryption? What do we decide about the complexity of modular exponentiation? When you're talking about n-bit numbers. It's n cubed. So the encryption is n cubed, where n is a number of bits. And that's a little bit slow, it turns out. So when after the midterm week, when we talk about this again, we'll see that in reality, RSA is only used for one step. Because the RSA isn't really fast enough, as fast as we'd like, it's used only for one of the steps in e-commerce. And we'll finish the story when we get to that.